No, I don't know.
Don't
So
worry, it's not necessary. Just
I
let me
think,
introduce him. So,
yeah, I think Anupam was Andrew Little's student, were you?
yeah.
Yeah, and that was at Sussex. So,
It was in Sussex long time ago, 97, 98.
uh, and then you were faculty at Lancaster,
Yes,
and now you're in Groningen.
that's true.
And Anupam has wide interests, mainly gravity and sort of quantum aspects of gravity. But this is the first time I'm seeing him uh, involved with experiment. So it will be good to hear. And I think the ideas, just by reading the abstract, sound quite fascinating and detailed. And so maybe that's the future of gravitational theory. So with that, Anupam.
Thanks. Thank you very much, Tanmay. It's really my pleasure to talk to all of you, although it's virtual. But I think the good thing is that we can still discuss physics. So today, what I will do is I'll discuss witnessing graviton via entanglement of masses, and soon you would realize that a very simple question, very innocuous question, that becomes a huge challenge from theory as well as from experimental perspective. So it's about how do you discriminate between classical theory of gravity versus quantum origin of the forces? So this is the kind of question which we would like to settle, which we would like to understand. Maybe the goal, the aim of from the theory perspective is very simple, very naive, but from the experimental perspective, you realize that it becomes very extremely challenging. And so the work which I started actually way back in 2017, and you could see that I was only lone wolf there because I came from the theory side, from the gravity side. Rest of my collaborators are coming from quantum systems, quantum technology, quantum information, and they're all experimentalists except Bose, who is a theorist from quantum information side. And on the same day, we had a similar paper, similar idea paper came in from the group of Oxford, Malletto and Vedera's group. And then we started working gradually in this topic, and we realized that, okay, there are various challenges, and how do we overcome these challenges? So this is what I'm going to share this exciting moment with all of you. Okay, so let me, yeah. So what is the vision? So the grand vision, of course, for everyone, not just for me, for everyone, I think in our community is the same, that how could we witness quantum gravity in a laboratory? Because gravity is sufficiently old subject. It's 400 years old subject. Quantum mechanics, quantum field theory itself is around more than 100 years old right now. We're fairly close to 100 years old. And, we are still asking the same question, that how to test whether gravity itself becomes is it really a classical system or it has some quantum origin. So this is the vision. And having said that, this vision is not going to get realized in 5 years time or 10 years time. It will take at least 2 to 3 decades. So that's the kind of aim we have, goal we have. So when I talk about quantum system, quantum mechanics and gravity, it means that I need to place something in superposition. So I need to test the superposition principle. And as soon as I try to create a superposition principle, I'm led to create a very tiny accelerator. So perhaps creating world's tiniest accelerator, which will become eventually like a graviton factory. From your colleagues for high energy physics, you have heard that people are talking about the Higgs factory, where you excite the Higgs and then you study the decay process of the Higgs and look at the various properties of the Higgs and branching ratios and things like that. So similarly, we are dreaming to have some kind of like graviton factory where you can excite quite a lot of gravitons, sufficient enough a number to see some of the witnesses, some of the interesting aspects, so that you can talk about its properties. So that's the vision, that's the goal, and let's see how far we move into this goal. And having said so, this is a fantastic time for all of us, because I believe that given the success of LIGO, Virgo, and also the future of gravity, like in Einstein telescope and LISA, which are all coming in the next couple of coming decades, perhaps this will be the decade or century even for gravity, because last century we have seen huge amount of progress in particle physics side, and perhaps this is direction which we have to move on. And of course, this has gathered quite a lot of pace in social media and all sorts of places. But this is a fantastic opportunity to bring completely two different subjects all together, from quantum information, quantum technologies, and quantum gravity coming all together. So this is a collaboration, a fairly small collaboration, but very wide. People are there from Israel, like Ron Fallman, and then Australia, Gerard Milburn, and Ryan Marshman, and then from America, Andrew Garachi. He's from Northwestern University, and my closest collaborator is Sogato Bose. Actually, we studied all together in from our undergrad days, so I've known him for a long, long time. So it's a fairly small, I mean, it's a small but very international group. But I hope that eventually this group will get bigger and bigger and will attract more and more excellent people from all over the world. So before we talk about quantum aspects, let's talk a little bit about the classical aspects of gravity. And you can ask the question that, you know, to what extent have I tested gravity at very, very short distances and very small time scales? So short distance gravity, you can test it. And in America, you have an excellent experimentalist, Adelberger's group from Washington. And he has gone into test a very short distance of just Newton's 1/r potential. And so as an experimentalist, what they like to do is that they like to plot the Yukawa potential with respect to the distance, where alpha is the strength of this Yukawa potential. And so you can see from this plot, this is the plot coming from 2002 paper. So this year's paper in the month of February, it appeared from the group. And you can see the yellow region is the one which is excluded. And now they have excluded this green region, green shaded region. And you can see that there are various constraints in the, on the plot. But the remarkable thing is that you can see that their constraints are there for very large values of alpha. For alpha 10⁻⁶, it goes up to 10⁻⁶. And in terms of distances, they can constrain the nature of gravity roughly around micrometer. So 3.8 times 10⁻⁶ meters or so. So what it means that if you convert that into some natural scale, natural units, and you convert that into energy, that turns out to be roughly 10⁻² electron volt to the power 4. And if you can consider the dark energy density, that's around 10⁻³ electron volt to the power 4. And you see that we are kind of like speculating the nature of gravity all the way from 10⁻² electron volt to the power 4, all the way to 10⁻27 electron volt to the power 4. That's the Planckian energy density. And in between, to be honest with you, there is no direct evidence of how 1/r potential behaves. Of course, there's some indirect evidences comes in, especially from LHC, from Atlas and CMS. They put indirect constraints on the nature of gravity coming from the Kaluza-Klein excitations and looking for large extra dimensions and from things like that. And that puts the constraint something like 8 to 10 TeV, which is roughly 10⁻⁻17 centimeters. But if you go further below 10⁻⁻17 centimeters, there are hardly any indirect constraints. So that's the status of gravity. And of course, whatever we do in the context of even cosmology, talking about the early universe cosmology, it is actually, we are taking a huge extrapolation, huge assumption behind the nature of the gravity itself, that either Einstein's gravity or some f of r form of gravity or some modification of gravity would work all the way. So even at the classical level, we know very little about the gravity. And then now the question comes that is gravity really classical or quantum? So it's a really hard question. So another way you can ask, where is the gravity Cheshire cat? So what it means is that to what extent can I see the gravity's quantum feature? But we know in the case of gravity, just with Einstein's gravity, we know that there's kind of a limit. I cannot go all the way to r equals to 0. There's a Schwarzschild radius corresponding to every mass. So if I want to see the cuteness of a cat, I have to go, when I say cuteness, I mean quantum cuteness. I have to go really very, very close to the Schwarzschild radius. And that's really very hard in any experiment in any laboratory. Of course, you can say that in LIGO and Virgo, we are actually seeing the gravitational waves coming from, we can probe the, fairly close to the surface of the horizon. We can look into indirect signatures like quasi-normal modes. We can look into echoes, and there are various ways you can put constraints, but nevertheless, you can never approach r equals to the 2m, the Schwarzschild radius. And that's really, really hard. And maybe if there is some, some quantum feature hiding there, you may get it indirectly, but that's, all these are indirect evidences. So let's do some kind of brainstorming, and you can ask the question, can you really isolate a graviton in a laboratory? If you can isolate a graviton, can you put the graviton in a quantum superposition? After all, you have done it for photons. Now it has become a regular feature in many of the laboratories throughout the world. And the answer is no. And it's partly because isolating a graviton is extremely hard job. The interaction strength of gravity itself is so weak that you can't really imagine doing this kind of in a small laboratory. Can we imagine that you can mimic some LIGO kind of feature, like coalescing two atoms and study how many gravitons you emit? Of course, you can think about this, and it could be possibly done. But again, you can see that the loss of gravitons here, you can just do back of the envelope calculation for the given mass of the atoms. And if you coalesce the atoms, again, it's not sufficient enough that your system would register, your detectors would register any gravitons. And the other thing which people have thought about it and have discussed quite in detail is that colliding ultra-relativistic masses. So of course, how ultra-relativistic, of course, people had thought about this in the context of LHC, where the center of mass energy can go all the way up to a couple of 10 TeVs, 17 TeVs. But then again, the problem is that the whole idea is that you collide the proton-proton beam, and if there is extra dimensions, then maybe you will form some black hole, and that black hole would eventually decay into standard degrees of freedom. You would register this, all these degrees of freedom indirectly, but unfortunately, that didn't really happen in the case of LHC. So again, with very ultra relativistic masses, the answer is yes and no. We have to rely on some new scale of physics in terms of gravity. So, well, I mean, extra dimensions would have brought a new scale, but unfortunately, since we have not seen it, so we have to really push the scale and see that in next linear collider or so, we can see this kind of phenomena or not. So, so what I'm going to talk today is that I'm going to take a completely different view altogether. And instead of chasing the ultraviolet, I'm going to go into the complete infrared aspects of gravity, because I see that more and more of the ultraviolet becomes harder and harder to achieve. So, so whatever I'm talking today sounds very much like a science fiction, but maybe that's tomorrow's reality. So the question we can ask is that can we witness quantum entanglement due to quantum nature of a graviton? And the answer is yes. Again, as I said, that it cannot be done in 5 years or 10 years time. It will still take at least 2 decades to 3 decades. And the idea is that you see that you have an accelerator at LHC, which is the circumference is something like 28 kilometers. You want to shrink it down all the way to something like an atom chip, which is like micrometer size. And you want to perform the experiment roughly at the micrometer size atom chip, where you can, these chips carry the currents. And with the help of the currents, you can create a mini accelerator. Perhaps you are going to create the miniaturest accelerator in the world to see some kind of quantum gravity phenomena. And so, so this is the thing which I'm going to talk to all of you, discuss about this. And as I said, I have had the luxury of discussing with many great minds of this decade and this century, perhaps like people like Abhay Ashtekar, Gary Horowitz, Frolov, Gabriele Vaniziano, Ashok Sen, Carlo Rovelli, Roger Penrose, Don Page. So many people have contributed and given their inputs. And of course, we are still learning from our experimentalist colleagues that how to overcome many of these challenges. Marcus Aspelmaier is the experimentalist in this game. So this is what I'm going to discuss the rest of my time. So just to keep an eye, keep some perspective. Like, look, I mean, we have seen the photoelectric effect all the way. We have understood its phenomena in 1905 in Einstein's famous paper. But it took almost 90 years to perform the experiment to show exactly that photon is really quantum. Of course, we knew that photon ought to be quantum from success of quantum electrodynamics. There was no doubt about the nature of the photon. But the fact that you could take the photon and you can put it in a quantum superposition in terms of either polarization or wavelengths or frequency, that took almost 90 years. It required a huge amount of technology. And nowadays, this kind of phenomena is kind of like routine in laboratory. And if you go to any big laboratory, maybe in ASU or in MIT, Colorado, everywhere, people can now do various kinds of experiments with photons now. But it took some time. So this is a good, kind of like lamppost to keep in mind that sometimes experiments do take some number of years to show the result. And so I have spoken quite a bit on the LHC side. So let me just briefly bring your attention again. How did you discover the Higgs? So what you did was that you took the proton-proton beam, you collided them and then you excited the Higgs. So Higgs was an intermediate particle or intermediate quanta. You did not just see the Higgs directly, but you saw indirectly in the sense that Higgs could decay into your four leptons or two photons. You registered those four leptons and two photons in your detector, and that's the way you could figure out the properties of Higgs, Higgs mass, Higgs decay widths, and all sorts of things. So something similar we are trying to do. We are trying to now accelerate the masses in a very, very controlled way, such that the gravitons are being excited as an off shell, exactly like in the case of Higgs. Higgs is excited in an off shell, so gravitons are excited in an off shell, and you want to witness that. The question is, how are you going to witness? In the case of LHC, we witness it with the photons and with the four leptonic events. So here the question is, how you're going to witness this graviton? How are you going to say that this is the graviton and it has a quantum in nature? So that's the challenge we have. So what I will do is that, so I will discuss this protocol. It's called quantum QGEM protocol, quantum gravity induced masses, entangled masses. So it's a QGEM protocol. And I will discuss how to read the witness, because that's the most important thing, that you have created an experiment, but you need to read that witness. And then there are associated challenges and future program. And if time permits me, I'll discuss a little bit about the theory aspects and how to motivate even quantum theory of gravity from the experiment, because quantum gravity has been traditionally always top heavy. So you build the theory and then you go to the bottom and discuss various phenomenology. But maybe now it's time that once you have an experiment in your hand, you can perhaps build the other way around as well. So having said so, I mean, has there not, there have been many contributors. Many people actually thought about these kind of problems. It's not just the first time I'm talking about. So people have, fantasized playing with gravity and quantum mechanics a lot over the years. And if you think about what people, this experiment of Cow, which is very famous experiment due to Colella, Oberhausen, and Werner experiment, which was done in mid-1970s, I think 1977 or 78. So what these gentlemen did way back in the mid-70s, that they considered the Earth's gravitational potential. So they took the, like exactly what we do in undergraduate quantum mechanics. You're given a classical potential, you take a ping pong, you want to quantize that ping pong ball in a gravitational potential. You want to see how the energy levels are quantized and things like that. So this is exactly what they did. They took the cold neutron, the potential was given by Earth's gravitational potential. They actually created a Alexander kind of interferometer, and they wanted to see the interference pattern, and they did see the interference pattern. And similar experiments have been now become quite routine in a laboratory. Way back in 2000 in Grenoble, what the scientists did was they took the cold neutron and they bounced the cold neutrons and they measured the energy levels of these cold neutrons because of the Earth's gravitational potential. So all these marvelous experiments have been done, and then you sometimes wonder that how could they can see this small gravitational effect. The reason they could see this because in the phase, in any quantum phase, what enters is your action divided by h bar. And in action, what enters is your g Newton. G is a very, very tiny number. H bar is a very tiny number, but their ratio is not. So if you tune your parameters, such as masses, the length scales in such a way that you can hit the sweet spot, and you can then you can see some interesting interference effects. And that's what happened in all these experiments. And now I think there are various experiments, suggestions are there from Stephen Chu and Stanford and Savas Dimopoulos. They're thinking about creating atom interferometer experiments, sending into space, even roughly of the size of meters and things like that. Similar experiments have been devised even to create a miniature version of that, which could detect gravitational waves. So this is called MIMAC, which can measure metric curvature, the rotation of Earth, and gravitational wave as well. So if time permits, I will discuss a little bit about these applications as well. Okay, so, but that was purely classical aspects of gravity. What about the quantum aspects of gravity? Something to do with quantum mechanics involved in gravity side. So as you can see this from this paper, Don Page and Gilker way back in the 80s had written a very, very interesting paper. And I believe that perhaps this is Page's the most important paper. If in future, maybe 3 decades from now or 4 decades from now, if an experiment wins a Nobel Prize, perhaps Page's name will be there. Given the fact that Page has done many interesting works, Page-Hawking transition, the Page time, in the case of black holes, these are all very nice works, but I think this work perhaps stands alone. although it's not very highly cited work of Page. It's, of course, it's still 200 plus, but Page has many more, elaborate, celebrated works as well. But nevertheless, the physics comes first here. So what they did at the time, way back in the 80s, is that they treated matter. So they asked the question, let's say that the matter is quantum. When they say the matter is quantum, what exactly did they mean? They meant that they could put the matter in a quantum superposition, a spatial superposition. They can create a Schrodinger cat state, for instance, with the matter. And now the argument was that, so it's in a lab frame, you sit down somewhere and say that if once you observe the system, observe the masses, it would collapse. The wave function would collapse. Either the cat is dead or cat is alive. And from here, you can measure the gravitational potential. And from the simple argument, they did some simple experiment. They tried to rule out the semi-classical nature of gravity. So what the semi-classical nature of gravity means is that you treat the matter component quantum, but the gravity part is purely classical. And that's what they were challenging. And keep in mind that this year's Nobel Prize soon is going to be given to Penrose, and all these fantastic theorems, singularity theorems, formation of a black hole, Hawking's evaporation, lack of loss of information, everything we discuss, entire Birrell and Davis book we discuss through on the framework of essentially effectively semi-classical treatment of gravity. So this is what they were challenging way back in 80s, that semi-classical treatment of gravity may not be the right way to go. Of course, they didn't go and prove that gravity ought to be quantum in any experiment. It was way too hard for them at that time. So, and as you can see from the abstract, so they didn't pretend that they could show that gravity is quantum, but at least they were saying that semi-classical treatment of gravity is not the consistent way to treat quantum mechanics and gravity together. And then way back in 2013, 2014, there was another very interesting event took place. Of course, now we know that it's not the primordial gravitational waves they had seen something else.
Can I just interrupt for just
sure,
a minute?
Sure, please.
I had read that paper some time ago. I thought the experiment was, how should I say, some strange kind of experiment.
That's true. That's true.
What, can you just quickly say what that experiment was? I don't remember.
So I think it was more of a statistical nature inference. So I mean, it's also, yeah, you're correct that it's a kind of strange kind of experiment, and no one has ever repeated that experiment. So the idea was something simple, that you can create a Schrodinger cat state for a matter. And that's technically, quantum people would call it a Noon state, that you can put the entire system to be in a quantum spatial superposition. So the matter is here or in here. And that you can create with even with what they were talking about, their masses were very tiny. It was not very heavy masses. And it is possible now to do it in laboratory. You can create a macroscopic superposition. When I say macroscopic, still they are very, very tiny, but you can do it 10 raised to minus 21 kilogram masses. You can put in a spatial superposition. And then you can, of course, choose a frame, and you say that, look, if the system is here or there, depending on that, your classical Newtonian potential will be different, because 1 over r will be different, because you're putting the state in a spatial superposition. So essentially, then you're treating the matter part purely quantum mechanically, that you can create a macroscopic superposition, but the gravity is purely classical. You're not touching upon the gravity side. And then you repeat this calculation many times, this experiment many times, and you would say that, okay, the system would collapse either here or there, that you don't know. It's a 50-50 probability. So from this perspective, they were actually arguing that the semi-classical treatment of gravity is not the most favorable way to
But it's hard to imagine Don Page actually setting up the...
No, Gilker. Gilker was his friend, was his colleague at the time. He set up the experiment, perhaps.
I also noticed that Paul might be at your talk, so he might have some more insights. But anyway, yeah. Paul Davies. Yeah.
Oh yeah. Paul. Yeah, sure. Paul would be. Paul knows definitely about this experiment, I believe.
Okay.
Good.
Thanks.
So. So then the next thing came, and so don't feel, just, stop me whenever you have to stop me, because it's good that we can discuss freely. So don't shy away. So so the next thing comes is with the primordial gravitational waves, and that time people thought that, okay, There was a huge excitement in the community that we might have seen these primordial gravitational waves. That would be amazing. And there were many papers, many people wrote many different kinds of papers, but one paper which stood up at the time was, again, your colleague Krauss and Wilczek. They had a very interesting paper saying that, look, you see the 2-point correlation function in the primordial gravitational waves, and that's the form. This is the form 64 alpha k square beta k square, where alpha k and beta k are the Bogoliubov coefficients, and then h bar enters. So h bar enters, and the capital H is your Hubble parameter, which tells you at what scale you had created these gravitational waves. So nevertheless, that's not important. The important thing is that the fact that h bar appears in 2-point correlation, and so that was a kind of indication that could we say something about the quantum nature of gravity, and could this gravitational waves tell us whether gravity is really quantum or not, if you ever detect it. But again, the problem comes in this kind of argument. If you're completely agnostic, if you say that, or if you're a diehard classical mechanics, you say that, no, I don't want to see gravity to be quantum. I want gravity to be classical. And if you have to convince someone like that, so they can come up with an alternative argument. They can say that, look, yes, in 2-point correlation, if you take the initial initial vacuum condition to be Bunch-Davies vacuum condition, you can get this h bar. But after all, h bar is a number, is a dimensional full number. So in principle, you can also mimic it in a purely classical setup. Of course, your initial conditions may be very, very crooked. Maybe you do not like such initial conditions. Maybe you can question that these initial conditions could be even God-given conditions. But nevertheless, if someone who is very much agnostic about this situation, can always come up and say that this can be treated even classically. It's exactly the similar kind of argument that if I drop a pebble in a peaceful lake, or the ripples which I see, these are purely classical. But maybe there could be some quantum origin behind these ripples as well, because these are the waves which we see. So again, just by looking at 2-point correlation, we cannot ascertain completely that gravity is really ought to be quantum here. It's a very good hint. Even I would like to see this kind of primordial gravitational waves, in future, but still it is not, razor sharp kind of argument which goes in favor of quantum nature of gravity. So when I say witnessing quantum gravity, what exactly do I mean? So what I mean is that I need to create a very razor sharp argument, because the subject is very subtle. It's very old subject. It's very old topic. Gravity itself is 400 years old topic now. So the argument which you want to set up has to be extremely sharp. And as you can see that from the astrophysical imprints, many people have tried to do this from the gamma ray burst, looking for time delays and various sorts of experiments they have set up. But there are also astrophysical uncertainties involved in all these experiments. The cosmological imprint, yes, if you see primordial gravitational, that will be very good hint that nature gravity is quantum. But again, there's a lack of statistics because there's only one universe. So what do I mean by razor sharp argument? What I mean is that I cannot come up with any, so this argument should be such that the classical world cannot replicate that experiment. So that's what I mean, that no matter whatever I do in a classical world, I can never replicate these effects. So that's the kind of razor sharp argument I'm requiring, demanding from myself. And I should have very good sharp theoretical and experimental witness. Witness should be such that I can statistically, certain that. So it should be statistically significant, such that I can say that, look, I can repeat the experiment in a very controlled way and say 99 point something, 4 sigma, 5 sigma effect. I can say that, look, now I can ascertain the gravity is quantum. So that's the kind of experiment I'm chasing now. So what are the key ingredients? So if you really want to chase this kind of, if you have very sharp, argument to chase, then you need very good ingredients as well. So the key ingredients here are the two features of quantum mechanics which can never be replicated in a classical world. That is the quantum superposition, creating the Schrodinger cat state, which inherently comes from the uncertainty principle. So the macroscopic superposition is inherently quantum. It can never be replicated in a classical situation or in a classical world. And the other is the entanglement of state. So let's go by the macroscopic quantum superposition. So when you superpose two masses, just from the linearity, so you are superposing also the curvature. Maybe the curvature is very tiny because the masses which we are talking about, they are very, very tiny. But putting this masses in superposition, you are also creating tiny superposition in curvature as well. So what is the current state of the art? So the state of the art is people can put macroscopic superposition with 10 raised to minus 21 kilograms. So in Marcus Arndt, that's the laboratory in the University of Vienna where Zeilinger is sitting. So what they do is that they have taken a Fullerene ball. So the funny thing about the Fullerene balls, C60 balls, are that buckyballs essentially, that you take any of these C60 balls, they're exactly the same. So the quantum properties are exactly the same. So you can take any two balls and create a macroscopic superposition. And now they can take viruses and bacteria and all sorts of things they can put in macroscopic superposition in a laboratory. And that they have kept. So the superposition was kept for roughly micrometer size. So the Schrodinger cat state or Noon state technical words, they created it for 10 micrometers size, roughly for time around a millisecond to second, depending on how well they can control the decoherence rates and things like that. But people have created the macroscopic superposition in laboratory. The second feature is the quantum entanglement. So I have given a few examples here. So in quantum mechanics, as you know, that either the states could be separable. So suppose you have got Alice and Bob, and if the states are completely separable, that means that you can take the states and you can separate them altogether. But then there is also a very interesting state, which is called entangled state, which you cannot separate it. So the physical example would be that sometimes we teach our undergrad or master student that the quantum vacuum is highly entangled. So what exactly do I mean? That if I have a Schrodinger pair production because of time varying electric field or magnetic field, I can create some particle creation. So these particles, electron and positron in this case, they are entangled. I cannot talk about the electron wave function separately and positron wave function separately, but I have to talk both of them, electron and positron simultaneously. So these are the examples of entangled state. So again, the entanglement is a very much quantum feature. It cannot be mimicked by a classical world altogether. So the microscopic superposition and quantum entanglement are the two features which we are going to use it now. So next comes how you're going to witness this entanglement. So as you know, in quantum mechanics, any entropy which you talk about is actually an entanglement entropy. So again, if you have two systems like Alice and Bob, you can construct the density matrix for Alice and Bob. You can talk about the reduced density matrix, say for Alice or for Bob, and you can compute the von Neumann's entanglement entropy. Now, if it so happens that if the entropy of A, system A, entropy of Alice and entropy of Bob, if they're exactly the same, then it means that they are pure states. But if they are not the same, then it means that the systems are entangled. And so this entanglement entropy is a feature of quantum correlation between Alice and Bob. But so you can measure the entanglement entropy, but it's also not so easy to compute this entanglement entropy in a laboratory. What people look for usually is the witness. That so what they say that, okay, exactly like what John Bell did way back in 60s, that he wanted to ascertain that quantum mechanics behaves really like a quantum mechanics and there are not other theories like hidden variable theories and things like that. So he created a witness in a very clever way. He created a witness which says that if so in this diagram on your left hand side, so on one side you will have all the separable states, all the states which are separable. If I'm playing with the two states Alice and Bob, then Alice and Bob would be separable on the left hand side, but Alice and Bob would be entangled in the shaded region. So W determines the some kind of the boundary between the separable and entangled state for a given density matrix, of course. So I have given a few examples. The first example I have taken is exactly the same as what John Bell did in his experiment for the Bell's inequality. So in his case, this is W is a witness parameter. And if W is greater than 1, you can ascertain that your experiment or your states, which you have created, which you have prepared in a laboratory, they're entangled. And sigmas are your sigma matrix, the Pauli matrices in sigma x, sigma y, sigma z. They are orthogonal directions. You have to take quantum correlation. So sigma x1 means system 1 and sigma z2 means the system 2. So you can also construct other witnesses as well. And depending on the nature of the witness, you can ascertain whether the state is entangled or not. So suppose if I create an experiment and I say that I pick up the Bell's witness. So in that case, I have to make sure that W has to be greater than 1 in order to make sure that the two states which I have created, they're entangled. So that's what the witness tells us. So this is the part which actually, this was not my expertise. I came from, as I said, from the gravity background, and this is the place where I learned something new from my colleagues, from those who were discussing, those who were playing with quantum information, quantum technologies, and quantum properties of system. And for them, it was well known. It's called local operation and classical communication. And this is the central part of the discussion essentially. So it's called LOCC. And it was first discussed by Bennett, Charles Bennett. I think many of you know. He's the father figure of quantum computer, essentially. Then subsequently, many people have proven this theorem. The theorem can be proven mathematically with the help of majorization of matrices and all sorts of things. So I'm not going to go into the mathematical details. I'm going to give you a very physical way to understand what is LOCC stands for. So LOCC stands for local operation and classical communication. So imagine you have got Alice and Bob. Alice has got a quantum system. Bob has got a quantum system. But Alice and Bob, they are talking to each other through a classical channel. So so the theorem tells us that if this is the case, if Alice and Bob, they are interacting through classical channel, then there's no way they can entangle the two states of Alice and Bob's. So the one way to understand it, suppose I give you a coin, you are sitting in Arizona and I'm sitting here in Northern Holland, and imagine the coin is quantum. So and the coin has Hilbert space too, because spin up, so heads up and tails down. And I request you to toss the coin billion times, and I do the same. I toss the coin billion times. So what will be the outcome? The outcome will be 50-50. 50% time you will get heads up, 50% time you will get tails, and similarly I would get it. So what it means is that our experiments done in two different separate parts of the world are done in such a way that I could not influence your outcome and you could not influence my outcome. That's what LOCC tells us, that we remain separable states. However, so once I came to know this theorem, immediately, this is the theorem which was introduced by Sogato Bose, my colleague, to me, and then I immediately said, well, if this is a theorem, then we can play around with this theorem. What happens if I have a quantum communication? If I set up a quantum communication between you and me, then what will happen? And if I do the same experiment, tossing the coin billion times your end and my end, what will happen is that I will be able to influence your outcome and you will be able to influence my outcome. As a consequence, what will happen is that this tossing the coin, it will not be 50-50, but it will be slightly different from 50-50, maybe 51-49 or whatever number you get, it will be different. And that's what violates your LOCC. So LOCC becomes local operation and quantum communication. So I have set up a quantum communication and I could influence your outcome. It means that your state and my states are now entangled with each other. They are no longer independent. I could influence you and you could influence mine outcome. And this is what the LOQC is. So anyway, so whatever we are talking within the light cone. We are not talking about something which is happening non-local outside the light cone. So everything is within the light cone. We are respecting all special relativity and everything. We are not violating any of these, special relativity. Many times you see that it's a non-local communication and things like that, but nothing from the field theory perspective, everything is happening within my light cone. Okay, so now here comes the crux of the argument. So you can say that, yeah, if you're diehard classical mechanics, you will say that, look, my classical potential, which I have derived, this 1 over R potential, Newton's potential, is purely classical. And there will be other group of people who would tell you that, look, I can derive the same 1 over R potential from a quantum picture. So what's the difference? Where the difference lies? So in a classical picture, of course, you can, what you imagine that the potential is given to you. And then in a fixed potential, you do all sorts of experiment. Exactly like what Chadwick did way back in 1920s. He took the alpha particle, he collided the alpha particle in a gold foil to understand the nature of the nuclear potential. So that's what you do. In a fixed potential, you try to you take the initial state and you go to the final state and you do the scattering event. But this is purely a classical potential. In a classical potential, you do the experiment. So that's the first term in your transition matrix. So TFI is your transition matrix going from initial to final state. Given a potential, you can go from initial to final state. This is purely a classical in nature, actually. But the second term in the perturbation theory, this is the bread and butter for the undergrad students, for those who do quantum mechanics part 1 or part 2, depending on countries. So the second term in the transition matrix brings us a very interesting, avenue. The avenue is now that there is an intermediate state J. So you go to initial to final state via this intermediate state J, and you are summing over all possible configuration here. So J is summed over. So this is the part. From here, you go from essentially from perturbative quantum mechanics to essentially quantum field theory. So the way you go if you sum over all possible configuration in the J, in the space and time, both, then what you get essentially is nothing but your Feynman diagram. So what the Feynman diagram does is that you say, now you are saying that the fixed potential, so Newton's potential is a fixed potential, Coulomb potential is a fixed potential. All these fixed potential in quantum mechanics or in quantum field theory has a new way of understanding, and that understanding comes in from the fact that you are exchanging a virtual quanta. So it's no longer a contact potential like in the classical physics, but there is a virtual quanta. So the assumption here is that you have an exchange of off-shell quanta between the two vertices at your end, at my end. Yeah. And as you know, the virtual quanta, they're very much non-classical system. So essentially within the uncertainty time relationship or uncertainty principle, you can excite this quanta from one end and borrow the energy from one end, and you deposit the other end. So it doesn't satisfy your classical equations of motion. So this is the off-shellness is inherently a quantum feature. So this off-shellness is the one which we are going to test in some sense. So now you can ask, what aspects of quantum gravity can you test in a laboratory? So I gave you an example. So suppose you're a diehard classical mechanics person and you say that, look, I just believe in classical physics, nothing else, nothing more than that. So for him or her, the potential is given to him or her. That's Newton's potential, or whatever corrections you're talking about, 1 over r square, or post-Newtonian corrections. And someone who is believing in quantum mechanics or quantum field theory, we are doing quantum field theory in a perturbative sense because the masses are very tiny we are talking about. So, for all practical purposes, we are doing quantum gravity in almost like a linearized limit. And for these people, what will happen is that you would say that everything is mediated via some graviton interaction. Through the X is your graviton now. And you can compute the one loop corrections or tree-level diagram, one loop corrections, two loop, and all these kind of corrections you can compute from a quantum field theory perspective. And these corrections are known. It's not that I have computed. It has been computed by Bryce DeWitt and many other contributions. Many other people have contributed it. Toft, Weltman, and now people even our colleagues from like Louis Byrne and all, they go up to even higher loops. So people have done sophisticated calculation. But then experimentally, so the difference is that in the classical case, now the difference is that classical case is exactly LOCC. You do not establish an entanglement between initial and final states. But in the quantum case, your initial and the final states, now they get entangled, and they get entangled via exchange of the virtual quanta, which is your graviton. And the same thing will happen for any Coulomb potential. Like if you do the Bhabha scattering or molar scattering to obtain the Coulomb potential in the non-relativistic limit, your off-shell exchange is the photon, and the photon will essentially entangle, the virtual exchange of photon will entangle the electron and positron, electron and electron, and positron and positron. So this is the difference between classical physics and now in quantum physics. And this is the feature we are going to now and try to understand that how to tap it experimentally. So both of these experiments at the tree level will give you the same phase, G over H bar. But as I said, that there's a subtle difference. The subtle difference comes in the entanglement. If you want to see something different to make your life exciting, what you can think about cosmic strings, and I thought it's a perfect example for Tanmay, because Tanmay is a real world expert in these cosmic strings, and he would appreciate this point very well, because if you take a cosmic strings, it doesn't have any tree level gravitational potential. So the only way you can, suppose you take two cosmic strings, the only way they can interact through gravitationally via one loop effect. But the one loop effect comes with the G square, because there are now 4 vertices, square root of G, square root of G, square root of G, square root of G. And the effect and the nice thing about it is that it's also one loop in graviton. So H bar comes in the numerator, G square H bar. But when you're looking at the phase, the H bar comes in the denominator, that cancels out, and what you get is G square effect in the phase. And G square is such a tiny number that perhaps it will take another century to detect this effect in a laboratory. But if it can be done, it would be wonderful, because it's such a pure experiment. Now you can find, you can find such a witness. It would be wonderful, really wonderful. But nevertheless, so for the coming couple of decades, perhaps we will not be able to be sensitive to G square term, but we are certainly sensitive to G over H bar term. And that's also I'm talking about not now, perhaps 3 decades from now. So this is what we are going to test in laboratory. Now, how you're going to do the experiment, that's the next challenge. So this is all about, but before that, let's just for a few minutes. So this is what about this local operation and quantum communication. What you realize soon is that it's not the local operation which is required. What requires is the quantum communication. So what is happening is that all that you require is the off-shell exchange, which is non-classical, which is non-commuting, which is based on non-commutating operator. As you know, as you realize immediately that the entire uncertainty, Heisenberg's uncertainty principle has now gone into your Feynman propagator. Feynman propagator encodes all the information of this Heisenberg's uncertainty in some sense. So, but nowadays you know all the machinery. You can compute the gravitron propagator around given background. You can take the energy momentum tensor. You can sandwich them together, and you can get the non-relativistic limit, the gravitational potential. So you can do it for various different kinds of theory. You can take f of r theory of gravity or any modifications of gravity, and you can play around. You can make that even interactions even non-local, and there also you can measure the gravitational potential. So all that requires is the quantum communication. So LO part is not so relevant, but what is relevant is the quantum communication. So you can introduce some amount of non-locality as well. And if time permits me, I will discuss that later. So this is the experiment. And you see that now the experiment is very different from the Collilla's experiment. In Collilla's experiment, the Earth was, just Earth was there, which is classical. Yeah. We never put the Earth in a quantum superposition. We cannot put the Earth in a quantum superposition. But now in order to replicate this scattering diagram, which I've shown you, so look into the scattering diagram, so incoming states and outgoing states. If I want to replicate this in a laboratory, I need to prepare. So essentially my chi mu nu is now quantum. So if chi mu nu's are quantum in two different spatial points, then I need to create some quantum state. I need to prepare my quantum state. How would I prepare my quantum state? So the way I will prepare my quantum state by the Stern-Gerlach effect. So I take the mass, and inside the mass, I embed a spin, and spin becomes my quantum ruler, because that's the perfect ruler. I can measure the spin up and spin down. So that tells me the nature of the Hilbert space. So I have created a macroscopic superposition on left-hand side and right-hand side, superposition for system 1 and superposition for system 2. And I allow them to interact gravitationally. Then essentially I would get exactly the same diagram as I've shown you, the scattering diagram. You see? So this is my experimental setup. So in order to do the experiment, as I said, that you have to embed a spin inside your mass. Now that mass could be so now I'm shifting towards experiment side. Now the question is, what kind of mass would you take? What kind of system would you play with? So right now the state of the art is to take diamond. Why diamond? Because diamond, the density is very large. It's very stiff in the sense. But not only that it has the stiffness and large density, but naturally occurring diamond always has some impurities. So whenever you go and buy from jewelry shop, the diamonds, you never get a pure diamond. These diamonds have certain defects, and these defects are nothing but in a video from the element perspective. There's a defect which is due to nitrogen or carbon-13. So you don't get always carbon-12. That will be your buckyball. Oh, sorry, it's not buckyball. C60 is the perfect buckyball, but you don't get the C60 kind of system. You get C12, you get C13, you get sometimes nitrogen, and nitrogen is N equals to 14. So naturally you get a valence bond. And that valence bond is nothing but your spin, electron spin. You will get an extra electron spin in the system. So any naturally occurring diamond always comes up with some defect. And that defect is a NV center. In technical words, called NV color center. Because when you shine the diamond, it can reflect the light. So sometimes you see the pink diamond or some other color diamond. Is precisely because of these phenomena in nature, that they can reflect lights. So NV center is very crucial. So it has a spin inside. So it becomes exactly like you're tossing the coin, spin up and spin down system. And so that what I have to do is that I have to create a macroscopic superposition for these two, for the two diamonds, and then I have to close the loop. And in the case of NV center, I know the Hamiltonian. I know how it interacts with the external magnetic field. In order to create the Stern-Gerlach, I need to have an inhomogeneous magnetic field, so I can control that magnetic field. But I also know that because the magnet has a certain magnetic susceptibility, and that will penalize me, because what will happen is that it will induce a magnetic potential, diamagnetic potential. So I need to take that into account. That goes by the volume. Larger the diamond, larger the magnetic susceptibility, larger the diamagnetic potential, and that makes B square term. And if you look into simple dynamics, you would realize that B square is a harmonic oscillator kind of potential, X square. It will try to destroy the coherence. And the B term is kind of like a friction term. It's a linear in order. So it will try to create the superposition. The last term, the NV center will try to create the superposition, V square will term to destroy the superposition. And the third term from the last is nothing but a zero field splitting. It doesn't depend on the magnetic field. So it behaves like roughly a cosmological constant term. And of course, gravity is always there because you're doing it a gravitational system. Of course, you can get rid of this mgz term if you can put your experiment in a freely falling lift or in a drop tower experiment. And eventually you would see that we need to go for a drop tower experiment because without drop tower, this cannot be done. And the first term is the momentum of the particle. I have not written down the momentum of the spin, but you can now write down the momentum of the spin as well, that how the spin precesses in presence of magnetic field. So you can write down the full Hamiltonian of the system. So the formidable challenge for us is to create this macroscopic superposition. As you can see that you have to use the Stern-Gerlach, and Stern-Gerlach requires this inhomogeneous magnetic field, but now you have to create a sufficiently large superposition to create this. So it's roughly it becomes like a miniature accelerator for you. So you have a magnetic field in the chip, and the magnetic field is created by the wires, and so by the current. You have to know the current precisely, so precisely that you can map the magnetic field and inhomogeneity in the magnetic field to create the macroscopic superposition, to create this essentially the Schrodinger cat state. And you have to close the loop as well. So these are the challenges we have. So this is the experimental setup. You have got two, system 1 and system 2. You can allow the system to evolve, and you can measure the spin correlation exactly, like as I said, that how many times you're getting, heads up and heads down, tails down. So you measure the spin correlation at the end of the day, and the spin correlation tells you the quantum correlation between the system. You will not get 50-50, you will get slightly different from 50-50, and that will tell you the witness whether gravity is quantum or classical in nature. So you can compute the entanglement phase.
Can I actually ask a quick question on the previous slide? You
Yeah.
have this statement in the upper right that I think is pretty important about if they interact only through the gravitational force. How are you going to make sure that's what's happening?
That's a very good question. I'll come to that point because that will be the huge background for me. And,
okay.
And that's a very good question you have raised, Cynthia. Thanks. So let's imagine that I have, as Cynthia pointed out very carefully, that here I have assumed that everything is purely gravitational interaction. There's no other interaction. So let's see if, with that, what are the parameters I can get. So in order to, as I said, that you can create a witness, so I have taken this particular witness, and in this particular witness setup, the W trace of W rho has to be less than 0 to ascertain that the gravity is quantum in nature. And for this particular case, you can compute the phase. Phase has to be roughly 2 pi, which is roughly order 1. And in order to make this phase roughly order 1, you require the masses to be now 10 raised to minus 14 kilograms. So you recall that I said that the masses were 10 raised to minus 21 kilograms in Marcus Arndt's laboratory. Now I have to bring it all the way from minus 21 to minus 14 kilograms. It's a hefty requirement. I have to create the superposition for roughly 1 second. I have to keep the superposition size of roughly of the size of 100 microns, and the interseparation difference and distance at the closest, d minus delta x, has to be roughly 200 microns to get the phase roughly order 1. And interestingly, to answer Cynthia's question, these are the parameters for which you can show that also the Casimir, because now the diamonds have certain dielectric properties. So that there is a Casimir-van der Waals interaction, which can also induced by, essentially, this is induced by quantum field theory, off-shell exchange of a photon. They can also entangle the two diamonds and two spins. But it just so happens that with this range of parameters, the Casimir and the dipole-dipole interaction, which goes as 1 over r cube, they are subdominant. So that's one way you can overcome some of these things, but we have to find some clever way because 10 raised to minus 14 kilograms is way too high of a macroscopic superposition, and we don't have the technology to do that right now. So I will try to ameliorate this problem further by imposing Faraday cage. So I have to construct a Faraday cage to get rid of the all the electromagnetic interactions.
Can I just ask? Yeah. I'm not completely clear on the setup. I mean, you're taking two of these diamond, whatever you call them.
Yeah.
And each of them is going through a Stern-Gerlach device, which is creating a superposition. And then the virtual graviton is between the two different ones.
Yeah. So the thing is that if you look into this plot, you can see that there are two paths. You don't know which path the information is. So you don't know which path the diamond is following. So let's concentrate on system one. In system one, there are two parts. So I don't know, as long as I have not seen it, it's like a Schrodinger cat state. I don't know where the diamond is. So it's purely diamond is now in a spin, superposition. So it could be here, it could be there. So similarly, I have got system two. So both the system one and system two are in a quantum systems now.
So what was the role of the spin inside the diamond?
Because spin can create superposition.
Oh, it was a spin up and a
Spin down.
so it's a superposition of spin up and spin down, or of two physical locations?
It becomes two physical location because
correlate
it's
back
embedded
up.
in the mass.
Yeah, okay.
So that's the creative part, that I'm putting the spin inside a mass
Hmm.
and I'm creating the superposition as spin, but as a result, my masses are also in superposition.
Yeah, and separate positions. I see.
So that is the part which is very, very crucial. It's good that you pointed out.
And then you have two of them, and then they are supposed to be exchanging gravitons.
Yeah.
I see.
And then they are entangling. And that's the entanglement feature I'm going to witness if gravity is quantum. Now, if you say that, no, I don't believe in gravity is quantum, or if the experiment does not give me the witness, I cannot conclude anything about the nature of gravity. So it's a very, very sharp witness, very, very sharp argument. Yes and no.
Okay,
And this
so
experiment will tell me for sure, if gravity is quantum, it will give me the witness. If it is not quantum, it will not give me anything.
okay. So then you're going to interfere them or something?
Yeah, so this is exactly the point, that I'm interfering them. So when I close the loop, then I create an interference at each end.
Oh, I see. So you'll get some correlation between if it's
Exactly.
up here, if it's up here, then it's up there. If
Exactly.
up here, down there.
Yeah.
Okay.
So this is this is a kind of like sure shot experiment. So that's the kind of razor sharp argument I was looking for. And that's the one which I can construct. But of course, now there are many, many challenges, as both you and Cynthia pointed out, that there are many sources of decoherence. I have not spoken that at all. So this is what I'm going to tell you. So then you need to take into account of all the effects of decoherence. And it's a nightmare. So first part is purely a theory that in principle, you can do this experiment, but now comes in the experimental side, that how are you going to realize this experiment? So there are many sources of decoherence which you have to take into account. And here I have parameterized all sources of decoherence, all sorts of unknown decoherences in terms of gamma. In order to have a witness, I need to have certain number. I need to put down some number, and that's the witness I will compute in my experiment, in our setup. But now in the course of decoherence, you have to keep in mind that there's a decoherence, as I've mentioned in this plot, that so you have created a superposition. So let's concentrate only one half of the superposition. So now you have to create an absolutely good vacuum. But even the best of best vacuum, you cannot have absolutely zero number density of particle. There will be some air molecules. If they hit your diamond, they can destroy the coherence of the system. So your vacuum has to be absolutely good. How good? It has to be as good as 10⁻⁻15 Pascal. That's the kind of vacuum actually you have in the tunnel of proton-proton collision in LHC. The best vacuum is right now in the LHC, and the next best vacuum is in the LIGO's experiment. So we need to construct something of that order. Perfectly good vacuum. You are doing the experiment with the atom chip. You're running through the wire. As soon as the wire gets heated up, it will emit photons. So that system can absorb the photon. System can even emit the photon. That can destroy the coherence. So I have to take into account of the absorption and emission of the photons inside this box, inside this apparatus. So all these things essentially will create destroy my coherence of the system. These are all known physics. These are all nothing beyond the Standard Model. These are just Standard Model physics will destroy the coherence of the system. So in order to create this, I have to really cool down the system. Keep in mind that the diamond is, after all, it's a condensed matter system. It has phonons. A phonon bath can destroy the coherence of the NV center spin. So I need to cool down the diamond. I need to cool down the diamond sufficiently below, say, 77 Kelvin, where I know that the phonon vibrations are very, very tiny. They will not destroy the coherence of the diamond spin for roughly 1 second. Even in the best of NV center right now in the world cannot create the superposition, cannot keep the coherence for nearly a second. It's now millisecond. I need to play a trick. what I have learned from people, from the experiment, is that the nuclear spin, the coherence is longer. It can live even for hours. So what you do is that you take the nuclear electronic spin, you create the Stern-Gerlach setup, convert the electronic spin into nuclear spin, which maintains the coherence, and then bring it back from nuclear spin to electronic spin to complete the entire loop. So we need to do all sorts of ingenious things in order to maintain the coherence. So not only that, you have to know how to prepare your initial wave packet. You have to neutralize any stray charges on the diamond. If there is some any stray charges that will destroy the coherence of the system, then you are not measuring the gravity, you are measuring the Coulomb interaction. You have to cool the diamond. You have to switch on the current. You have to know the current precisely so that the magnetic field profile is exactly correct. I mean, you cannot destroy that magnetic field fluctuations. You cannot allow any fluctuations in the magnetic field. So you have to put the current in a superconducting current. So with the current is in a squeeze state. So in order to do this experiment, I need to find another technology where I need to squeeze my current even. And that technology still does not exist at the temperature which we are talking about. And then you have to close the loop. There's a famous problem due to Scully, Ongle, and Schwinger, that in a Stern-Gerlach setup, you have to make sure that the coherence of the spin, there are two spins. Now the spin coherence is maintained when I do the interference. So I created it and then I interfere it. And I have to make sure that the spin correlation is there. Otherwise I cannot read out anything. And then eventually I have to read out this, the spin, which is up and down, and then I can build a, experiment. So there are many challenges. You open up the book from Griffith's book or Jackson's book, you give me the page number. That's the challenge for me. That's the background for me, because electromagnetic interaction is way too strong, 36 orders of magnitude stronger than gravity. So they're ready to destroy your experiment, but you have to beat those, bounds. So one of the way, which Cynthia already pointed out to me before, that how you're going to ameliorate the electromagnetic interaction. So one way, what you can do in any laboratory, if you go in for this kind of experiment, even your refrigerator can cause a trouble because that's the electromagnetic radiation. So what you do is that you put in a Faraday cage, or you take into account of whatever electromagnetic interactions are there locally in your experiment. So the best way is to do the Faraday cage. And here also what you have to do is that you have to create a Faraday cage in between the two systems, the two superpositions, so that there's hardly any leakage of your electromagnetic interaction from one system to another system. Of course, having put the conducting plate, now what will happen is that there will be interaction between the diamond and the conducting plate. They will interact. There will be a Casimir between them. So that you have to take into account. So once you take this into account, this changes the geometry a little bit. So the initial on your left-hand side, there was no Casimir plate in between. And now if I put a conducting plate, so that depends on how thick the conducting plate is, what is the material of the conducting plate, whether it can withstand the temperatures and all sorts of rigor of the experiment you have to take into account. So if you take all these things account, what we have found, that you can ameliorate some of the parameters. You don't require 10 to minus 14 kilogram superposition. You can bring it back to 10 to minus 16, minus 15 kilogram. The initial superposition, which was 200 microns, you can bring it to 20 microns. And the pressure from 10 to minus 16 Pascal, you can go to 10 to minus 15 Pascal. Now you will say that, look, these are just order of magnitude numbers changes. It may not impress you, but even though these are order of magnitude numbers, these are huge gain from the experimental perspective, because I have told you that what we have done so far is 10 to minus 21 kilograms. And now if I can say that to the experimenters that I can do the experiment with 10 to minus 16 kilograms, I have to go maybe 5 or 6 order of magnitude to catch up, which is still better than catching up 7 orders of magnitude to create the Schrodinger cat state. So there are all these advantages, but you see that as soon as you try to solve one problem, you are bitten by other side of the problem. Now the phase which I was measuring order 1 phase, I cannot measure order 1 phase. I can measure only 0.01. So 0.01% of the initial phase I can measure. So it means that I need to repeat the experiment 1 over square root of n from the RMS. So if the phase is 0.01, it means I have to run the experiment. If the experiment runs for 1 second, roughly 10 to 4 seconds. It means roughly close to half of the year. So I have to run the experiment half of the year to get the phase, which is roughly order 1, in order to infer the data, whether the witness is good enough or not. So all these kind of problems, small problems, creep into the problem. So you can measure, as I said, that for all these parameters, for all the decoherences, you can measure the witness. And here on your right-hand side, the witness parameter is measured with respect to number density of the vacuum and the mass of the superposition. And you can see that x-axis is your mass of the superposition, and the y-axis is your how good your vacuum has to be. And that roughly corresponds to 10 raised to 7 per meter cube volume. Number density corresponds to roughly 10 raised to minus 15 Pascal. And the pink region is the highest, largest witness parameter, and red is where there is no witness between in the experiment. So you cannot establish anything. So you are chasing this pink region of your parameter space. And on your left-hand side, this is all the decoherence rates. If you take into account, if you keep the experiment for roughly 1 second, you see that you have to really go to the temperature below 1 Kelvin. So then only you can perform this experiment. So what you need is you need a dilution fridge. With normal refrigeration, you cannot do the experiment. You have to really go into the dilution fridge where you can go below 4 Kelvin to perform this kind of experiment. So there are various challenges like this. You can also talk about whether the gravitons which are floating around, even the LIGO or gravitational waves, whether that will destroy your coherence or not. But that turns out that's not the problem, because the gravitational interaction is so weak that graviton-induced decoherence is very, very tiny in this case. So that's not a point of worry for us. The next major worry for us is that gravity gradient noise, because after all, it's a finite size box. And finite size box means there are finite size effects, which you have to take into account. Even a butterfly passing by my experiment will induce a Colella phase to my experimental setup and can destroy it can dephase my system. So I have to make sure that I have to create an exclusion zone, how far I have to be from the experiment such that there is no disturbance to the experiment itself. It's exactly like, if I do the experiment in Geneva, then I have to be careful even how much the Lake Geneva water changes, because even that will give you, because that's a seismic noise for the experiment. And my sensors, my interferometer has become one of the best sensor on Earth. It can sense if the water level changes. If the TGV passes by, it can sense it. If the bird is passing by me, it will sense it. If the snake slithers by the experiment, it will sense it. So everything can sense and destroy the coherence of the system, can destroy the phase of the experiment. So I need to create exclusion zone. So on the right-hand side, so this is what I have plotted, the various gravity gradient induced terms which can destroy the phase. And on your x-axis, there's an exclusion zone. And what you find is the region where the seismic noise and the jerk crosses each other, which is roughly around 5 meters or so. I need to create exclusion zone roughly from 5 to 6 meters. And on the left-hand side of your, there's a plot which tells you how big the experimental capsule has to be. And even depending on the capsule and the mass of the capsule, it depends very much the gravity gradient noise, because after all, the gravity gradient noise depends on the size of the system, how big your system is in your experiment. And that depends on what is the embedding pressure in the system. So maybe this plot may not tell you much, but this artistic plot is a very schematic design, will tell you how demanding this experiment has to be. So imagine now you have got, so in order to do the experiment, what we have realized, we cannot do the experiment on the ground. That's impossible, because there's a huge Earth's gravity itself, which will destroy, which will create the, dephase the system. Any small acceleration can destroy this phase of the system. So if I perform the experiment in a drop tower standing on Earth, what is happening is that I cannot stop, say, cars passing by nearby or planes passing by. It's exactly like LIGO. Even LIGO has a exclusion zone. So even the small, because in our case, this exclusion zone is not so big. It's around 5 to 10 meters. So the best thing is to go underground, where the seismic noise is very low. So you have to go to a particular place on Earth where the seismic noise is low. So you see that the real experiment which is happening is in the pink box, which is the innermost capsule. That is embedded in a capsule. And inside, the pressure has to be 10 raised to minus, the very inside of the capsule is 10 raised to minus 16 Pascal. Outside the capsule is 10 raised to minus 10 Pascal. And outside, even outside that capsule, the pressure has to be something like 10 raised to minus 9 to minus 6 Pascal. Why? Because you're dropping the system. Even an air pressure can give you the drag. So you have to take away the air pressure so that even the freely falling lift can be realized as much as possible. So even this design could change. Maybe now I have put 2 layers. Maybe in the eventual design, I have to put 3 layers or 4 layers of vacuum. So all these tells us that this experiment cannot be done by in a simple laboratory. I need to go for something with international collaboration. and I have to go to the depth of roughly 50 to 100 meters, because you know that G Newton is roughly 10 meters per second square. Even in 1 second, you reach very quite a couple of hundred, 5, 6, 7 meters you displaces. So you have to take all these things into small things into account to perform the experiment. And recently we are now testing we are doing the first experiment, the Stern-Gerlach experiment. So we are coming from the theory side. Our main experimentalist is Ron Fallman from Israel. So that's the technology we are going to use, this atom chip experiment. So with the atom chip, we are trying to create the first interferometer. So right now with the current technology, we can do exactly what Marcus Ahn did, 10 raised to minus 21 kilogram with rubidium atoms. But now from here, 10 raised to minus 21 kilograms, we have to go all the way to 10 raised to minus 15, minus 16 kilograms. So that's tall order, but nevertheless, we have to improve the embedding of the wires and all sorts of things in the future to build the interferometer. So I think, how much time do I have? Maybe I have over spoken already, but if I have 1 minute or so, then I'll wrap up very quickly.
Yeah, sure.
Yeah.
Absolutely.
Okay, so let me quickly run through. So you see that these are now the best sensors ever built on Earth, because the experiment is so sensitive that it can even sense the jitter of 10 raised to minus 12 meter per second square. So if there is a jitter of acceleration which 10 raised to minus 12, 10 raised to minus 13 meter per second square, it can sense it. If it can sense such a small acceleration, it can also sense gravitational waves. So you can build a system with this kind of apparatus, which can actually sense the sub-hertz gravitational waves. And if you right now, LIGO cannot go below hertz. So if you go for sub-hertz gravitational waves, you are sensitive to the memory effect of gravitational waves, that what people are now talking about, that maybe you can be sensitive to the very long wavelength gravitons, which are very soft gravitons. So you can see maybe you can feel the effect of them as well. So from the theory perspective, what it tells you, that if gravity is really quantum in nature, I don't have to go to perform experiment in the UV. Even in the infrared, I know, because of the inherent nature of quantum nature of gravity, even the matter are entangled, because matter is inherently quantum. So we are all entangled. And in the infrared, I can probe the nature of gravity, how the entanglement is building up. So that's something which is a new handle for experimental tool for all of us from the quantum gravity perspective. As I said, that I briefly touched upon local gravity and non-local gravity. So you can take any form of f of r gravity and you can perform the experiment. You can test the nature of the gravitational potential. You can test 1 loop corrections, 2 loop corrections, depending on how sensitive you build the experiment. You can even see how what is the rate of growth of entanglement. And because of the universality, the fact that gravity has a universal 1 over r fall, you find that there is some universality in the rate at which the entropy also builds up. So on your left-hand side in the lower panel, I have got 2 plots, entropy versus the number of sites, the Hilbert space essentially. So when where n determines the number of Hilbert space for 1-dimensional system and for 3-dimensional system, and you see that the behavior of growth of entropy is pretty much universal, which is a kind of logarithmic behavior. So these are some interesting infrared quantum nature of gravity you can probe. So let me conclude. I'm coming close to my conclusion that this is the protocol which we are calling QGEM. But you see, this is one protocol which unites many different wakes of science. You are talking about, I touched upon a little bit of the material science. We are doing with the diamond, but maybe tomorrow we can come up with a better material. We can construct our material according to our own, I can change my diamagnetic parameter. I can check my dielectric, constant. I can maybe manufacture a new material altogether in order to perform this experiment. So not only that, I'm talking about the Casimir potential. There's a patch potential. There's a huge industry with this defects, which I can try to understand. I can try to understand the behavior of phonon interaction sufficiently low temperature at below 1 Kelvin. Of course, I'm dealing this experiment with atom optics, levitations. Not only that, I can also do beyond the standard model physics. So I can test even the non-relativistic form of QED. Instead of charged particle, if I go to Alice experiment in LHC, which creates my heavy charge particles, I can if I can trap those charged particles with my atom chip and create a Stern-Gerlach apparatus, I can essentially be sensitive to my QED effect. I can look into 1 loop corrections in QED because QED is much stronger effect than gravity. So I can test even those kind of phenomena as well. Hidden sector photons or axion physics I can probe. But beyond all of this, I can test the foundations of quantum mechanics. I can test the foundations of quantum field theory. I'm testing the foundations of gravity. And en route to this, as you know, that Penrose, this year's Nobel Prize winner, had also proposed Penrose's collapse, the spontaneous collapse of the wave function. He believes that maybe the gravity is different and wave function collapses instantaneously. So you can test some of these hypotheses as well, although no one can prove it from the first principles, but you can test some of these things en route to that. And also you can test gravitational waves. So one protocol which can do many different aspects of fundamental physics. And so I believe that this is a conclusion in future that perhaps testing quantum gravity is the final frontier. And hopefully this coming decade or coming century will, with the improvement of technology, will definitely help us to reach that goal. So let me thank all of you. Thanks a lot for your attention, and please feel free to ask me questions, and I'm available. Thanks.
Thank you, Anupam, for that inspiring talk. So if there is any further question or comments, please go ahead.
Yeah, I was just
I have a
gonna
quick
say-
question.
Sorry.
Oh, sorry.
Go ahead, Henry.
Okay, I have a quick question. Maybe I missed it, but how do you account, due to all the materials using and so forth, natural radioactive decay? Maybe I missed that, but how would you account for that?
Natural radioactive decay. So I'm playing with the material right now. Best material is diamond. So I'm not playing with any radioactive materials right now. Maybe you can elaborate a little bit what you have in mind, then I can perhaps answer.
It looked like you were using a semiconductor chip type device.
Okay, so yeah, so essentially, so these chips, I have never come across, to be honest with you, this radioactive aspects of the chips so far, but maybe you know better than me in this aspect, and you can tell me a little bit more on that. But what I know is that these chips now, the way people do it, people can embed wires on these chips. And depending on the nature, how do you engineer it? Even you can go for 2D, or you can do a 3D printing of the chip as well. So what happens is that you can create a magnetic field profile. And in the magnetic field profile, you have to create sufficiently large magnetic field gradient to realize the Stern-Gerlach kind of effect. Of course, having said so, we have not realized to create large macroscopic superposition. We have created this in this experiment, with atom chip, which I was showing you. You see we are talking roughly around micrometer superposition, which is kept for roughly 450 microseconds or so, roughly 500 microseconds. So it's not that we have managed to create a very large macroscopic. It's still very tiny, but we have to open up, we have to improve the technology so that we can go for even larger superposition. So that's the challenge we have right now.
Okay, thank you.
You're welcome.
So I had two questions. One was that you'll have to do this experiment many times, right? So that, so if you were like the one that you were thinking of dropping, and so yeah, so okay. The other point was that you're trying to exclude electromagnetic, like photon exchange.
Yeah.
But of course, there could be unknowns, like you could have an axion exchange.
Of course.
Right?
Yeah.
So if you see a signal, then you don't know if it's gravitons that are being quantized or whether you have something else.
Absolutely. So yeah, you still have this. Essentially, then in order to see the axion, there could be some fifth force. There could be some physics beyond the standard model. So here, whatever background I have computed so far with the known physics, and then I'm chasing the graviton. But yeah, this risk is always there that if there is some fifth, some new force comes into the game, then they can actually, because I don't know the interaction rate, I don't know what is the mass of the field. So all these things, uncertainties can creep in. And yes, I agree with you. These problems will always be there. So, but then the question is, if you have to create this, kind of experiment, then you would also create the experiment maybe in the neighboring room with some electromagnetic charge particle to test if there is some, photon, if there's axion exchange or something like that is happening also or not. So yes, it's true that you have to be a bit more careful.
Yeah.
Well, that's less than a risk, right?
Mm-hmm.
is less than a risk. If you can associate the interaction to a fifth force, that's even better.
No, I mean,
That proves
anyway,
That's also
anyway, these will be new results. This will be new discovery.
Yeah.
So even if you can measure fifth force or maybe the dark matter in this way, it's a new, sometimes this is what science is. It's about serendipity. Maybe I've been trying for quantum gravity in the process. I may get some new physics as well. So yeah, but
I have
what
a question from
absolutely
the
correct.
I have a question from the naive from a theoretician point of view about the experiment. So probably it's very stupid. So a lot of your challenges come from the fact that, first this is free falling system. So you have to make a huge vacuum. And the other, you have to account for all the noise coming from human activity and the activity in the earth. So isn't it easier to run this experiment on a satellite or something on the International Space Station when it's actually just free falling all the time?
That's
and
true.
you have the noise under control.
That's true. But you would be amazed to hear that even in the ISS, International Space Station, the G is not completely zero, but 10⁻³ times the Earth's G. So it's not sufficiently good enough. So I still have to have a dedicated mission where I can do like ELISA kind of LISA experiment type of experiment, but the cost immediately shoots up. So because of sending through the rocket and all, and because it's a control experiment, so the cost will be something like billions. And now maybe with $500 million, I can do the experiment in a drop tower, underground, and which will be also controlled. Of course, this at some point, these kind of experiments become so expensive that as a poor physicist, we have to count where to sacrifice, what to sacrifice. And you see that whatever I'm talking about is nothing but in California, that's what people are developing, quantum computer. They're also built on quantum entanglement. Except now they're not playing with these massive systems or macroscopic spatial superposition. They're playing with the superposition in the momentum space. But you see the money they have they have a huge investment. We are the poor cousin of the same physics, where we want to do fundamental physics, but of course we don't have money. And every time we are questioned that how to compromise, what to do, and this kind of questions. So I think I was also asked this question that how much will it cost in one of the funding agencies, and roughly I think at that time I gave them some rough estimate, which was something $500,000. It will still cost $500,000 because I need to go to a very seismically quiet zone. And there are not many, there are a few places geographically people have mapped out various regions. Even LIGO and Virgo had to do, they have to put sensors everywhere to sense, to counter the, all sorts of gravity gradient noises. So you have to go to these kind of sites. You have to go to 50 to 100 meter and dig a hole, and then you have to create this drop tower. So of course, these things are going to be expensive affair. Plus, on top of that, you have to create the macroscopic superposition. That itself will take some investment. So it's not something which one country's funding agency can do it. And that's one of the reasons I have I'm going up every country by country and talking to colleagues in America, like today I've done with you guys, and trying to convince that if you think sufficiently interesting and if you want to join for future, of course, the dedicated mission of 2-3 decades, I mean, you're most welcome, because what we have realized that sitting in, just one country, we cannot do this experiment anymore. But the advantage is that this is the kind of experiment which will be like exactly like Bell's test. So Bell's test was to prove whether nature behaves like quantum mechanics or not. And here is the equivalent of Bell's test for the case of gravity. So it's a very razor sharp. There is no, of course, having said so, there are, as Tanmay pointed out, that there could be axion exchange and things like that. There is still some uncertainties there. But barring those very tiny uncertainties, you can narrow it down very, very much.
Okay, well, very interesting, very ambitious. I think, but good.
But yeah, but the biggest challenge for us is to now, is the money. The funding is the biggest challenge for us. Sustained funding we need. It's like, LIGO and Virgo, what it used to be, say, 20, 30 years ago. But I think here also we need sustained challenges, sustained finance support. But if we can get it, then I think, en route to this, we can do many small experiments. Like, as I said, that you can do the experiment with a charged particle, and then you can be sensitive to hidden sector photons or axionic physics, because now you're talking, because if there is a loop effect, you can capture the loop effect in electromagnetism, because of the alpha EM is very strong compared to gravity. So if there's unknown physics in the loop, then you are sensitive to that. So essentially what I'm talking about, this diagram. Yeah. So suppose in the case of now, I replace the neutral particle by charged particle, then I'm sensitive to this loop diagrams wherein you have a, either axion is running in the loop, or maybe the hidden sector photon. So you can constrain those kind of physics, because they will change the entanglement phase and the correlation. And you can, from the correlation, you can say something about the nature of fifth force as well. So these experiments will be perhaps easier to do, but then because of these are charge system, the decoherence is too much. So you see that you want to do one experiment, but also you have to think that what bites you. So here, what will bite me is the decoherence rate will be very quick, because electromagnetic, everything interacts with electromagnetic, charges. Electromagnetic interaction is so strong. So maintaining the superposition will be the biggest challenge for me.
But these people who do precision experiments,
They do to some extent. Yeah.
Loops. And we actually have a new faculty joining us.
I see.
Who does precision experiments.
So yeah, I mean, many people do precision experiment looking at the EDM constraints and all. So they try to do they trap the ions and they play with these ions. So yes, so these are new avenues where we can. It's completely a non-relativistic regime, but even the non-relativistic regime has very interesting physics. It hides, and maybe we can tap those physics now.
Yeah, very good. Okay, I don't have any more questions. I have to read your paper.
Right. So thank you very much, Anupam, and for staying up to these late hours. So yeah, thank you. And then that would be in the seminar.
Thanks. Thank you very much. Thanks.
So thank you all. Have a good night and have a good day, the rest of us. Bye-bye.
Bye.
Oh, by the way, Anupam, I'm posting this on YouTube.
That's
but sometimes I just post it, okay, because some people couldn't attend.
That's fine.
And one of them was Paul Davis, but I see he actually could do it. So sometimes I post them, but I don't put it public. I just you can upload YouTube videos and then just send the link to people that you want.
That's okay with me. Yeah.
Or you can, okay. Then I'm going to make it public, and then you can. Sure. I will send you the link later as well.
Okay. Good.
All right.
Thanks. Thank you
very
much.
much.
You're welcome.
Bye bye.